All right. Let's look at another polar equation that we can graph. So remember last time in the last video we looked at a cardioid. Okay, and you know it had a sign in it, and our technique was to just go ahead and graph it as if it were like a Cartesian equation, and then use that to help us draw the polar curve. And since this one has a cosine in it, we're going to use that same technique. So first of all, let's go ahead and graph it as if it were just a Cartesian equation, and we'll use that to help us. Alright, so we know that if we have cosine of 2 theta, that 2 as a coefficient in front of the angle is going to make the period be 180, or pi radians instead of 2 pi or 360. Okay, and so, you know, let's put this at 2 pi, and we'll put this at pi. Okay, and so we're going to see one full cycle of the cosine in pi radians. Okay, so let me divide this. Pi over 2, pi over 4, 3 pi over 4. Okay, and it's going to look like that. Here's 1, here's negative 1. And then it's just going to do that again. Okay, so we have basically 2 periods of or 2 cycles of the cosine 2 pi radians. Okay, so that should help us as we're trying to draw our graph. Okay, so here is 1, this is theta, and this is r. This is going to be a polar graph. So this is Cartesian, and we'll see what that does on the polar coordinate system. Okay, and so I'm going to just kind of mark in our pi over 4 degree lines in here, since we have those on our graph, so we're going to need to see where they are here as well. So I'll just kind of lightly draw those in. Okay. Okay, so at 0 degrees we start at 1. Let's say this is 1. That's 1, and this is negative 1. This is negative 1. Okay, and as we go from 1 to pi over 4, we are decreasing from 1 to 0. As we move from 0 degrees to pi over 4 degrees, we're decreasing from 1 to 0. Okay, I'm going to put a little arrow in that so you can see how it went. Okay, I'm also going to just go ahead and do the order that these came in here, because when you see this at the end, what order did this all happen in? Okay, and then as we go from pi over 4 to pi over 2, so here's pi over 4, here's pi over 2, as we're going this direction, so we're going to get negative values. So instead of being in the first quadrant, we're going to get stuff that's over here in the third quadrant. Okay, negative values from increasing towards negative 1. So when we get up to, pi over 2, we're going to be at negative 1. Okay, so we're going this direction like this. So this is the second. Here's 1, here's 2. All right, and then as we move from pi over 2, so here's pi over 2, okay, to 3 pi over 4, we still have negative values, so instead of the second quadrant, they're going to come down here in the fourth quadrant, and back towards 0, from negative 1 to 0. So it's going back towards 0. So this is the third one. All right, and then from 3 pi over 4 to pi, okay, we have positive values that are increasing to 1. Okay, and so we'll be increasing from 0 to 1. Okay, so when we get to pi over 2, we're 1 away from the pole. moved this way. This is the fourth thing. This is number 4. And then we move from pi, okay, to 5 pi over 4. That's these angles here, third quadrant. Okay, we're going back from a positive 1 towards 0. So still staying in this quadrant towards 0. So this direction, this is the 5th thing. All right, and then as we move from pi over 4 to 3 pi over 2, that's pi over 4 to 3 pi over 2. Okay, we're getting negative values again, 0 to negative 1. Being in this third quadrant, so we have negative, since we have negative values, they're going to appear over here in the first quadrant. So they're going towards 1, so it's going to come up like this. This is the 6th, we're on number 6. Yep. Okay, and then as we move from 3 pi over 2 to 7 pi over 4, so that's here. We still have negative values, so instead of being in the 4th quadrant, they're going to be back over here in the 2nd quadrant. From 1 down to 0. This is the 7th thing that happens. And then finally, as we go from 7 pi over 4 up towards 2 pi, we're back in positive values, so we're going to stay in that 4th quadrant, increasing from 0 to 1. So this. And that's the 8th thing that happened. Here's number 8. Okay. Okay, so we get this is called a rose, and if you see why, I mean, it's at least looks like a flower. Okay, so we have this cardioid, we have this rose that looks kind of like the petals of a flower. Yep. Now, when we graph these things, polar curves, it's often advantageous to look at the symmetry that's there. That can help us figure out, you know, if we thought about some of the symmetry, we might have only had to draw part of the curve, etc. Okay, so here are 3 different for how we can look at different kinds of symmetry. Okay, so if a polar equation is unchanged when we replace theta with negative theta, the curve is symmetric about the polar axis. And we have a picture. So let's say, you know, I have a point at, here's theta r. Okay, and if I put negative theta in instead, I still get r. So the equation is unchanged. I get the same of r. So if I put negative theta in and got the same r, notice that those points are just, okay, basically a reflection over the polar axis. So it's symmetric about the polar axis. Okay, so that's a visualization of what happens in this first case. Okay, in the second, if the equation is unchanged when we replace r with negative r, or when theta is replaced by theta plus pi, then the curve is symmetric about the pole. And when something is symmetric about the pole, that means that we can rotate it 180 degrees and exactly the same. Okay, so here's an example down here. Okay, and so if I have the same angle theta, okay, and r and negative r, both map to that same theta value. Okay, so it's unchanged when I've replaced r with negative r, so it still has the same theta. So here's the angle with the positive r, here's the angle with the negative r, and so that you can see if I just rotated it 180 degrees, just, you know, this point goes here and this point goes here. Okay, and it's pretty good if we just add pi radians that you're rotating in 180 degrees, so that will also make it symmetric about the pole. And the last case is if the equation is unchanged when theta is by theta, or pi minus theta, then the curve is symmetric about the vertical line, theta equals pi over 2. So theta equals pi over 2. Okay, if you think about it, theta pi over 2 degree angle, that's this line right here. Almost as if it's like the y-axis if you overlaid a Cartesian coordinate system on top of it. Okay, but we don't have a y-axis in a polar. Okay, so here is the angle theta. Now if I do pi minus theta, that's going to be this angle over here. Okay, so if this angle and this angle give me the same r value, okay, then I'm just, basically that's a reflection across this vertical line here, degrees, or at pi over 2 radians. Okay, so that's the symmetry used there. We can look at those kinds of symmetries, and sometimes you can just draw half or part of a graph and use the symmetries to figure out what the rest of it would look like. So now that we've looked at polar equations, we want to be on them. So let's say we wanted to be able to find a tangent line to a polar curve written r as a function of theta. So what we can do is we can just regard theta as a parameter and write parametric equations to be an equivalent form of the polar equation. So we have, we know that x equals r cosine theta, and now r is function, so we can substitute whatever function in there and multiply that by cosine theta, that coordinate in a Cartesian system. Similar, if we want to basically convert this to its Cartesian equivalent, we would take r times sine theta to get the y coordinate. So r is really just some function of theta, and so multiply that by sine theta to get the y. And use what we know from the previous section, section 10.2, about how to find the derivative. If I want the derivative of y with respect to x, I can just use the parametric equations and take the derivative of y with respect to the parameter and divide that by the derivative of x with respect to the parameter, and that will give me the dy dx. Okay. Now, one thing to notice is that we have to, because these are a product, we're going to have to use the chain rule on these. So let's just, very generic. So if I was doing dy d theta over here, product of f of theta times sine of theta. So I need to do the first, f of theta times the derivative of the second, which is cosine theta, plus the second times the derivative of the first. Okay, so that would be my derivative dy d theta. Divide that by dx d theta, and so I would have there first times the derivative of the second of theta times negative sine of theta plus second times the derivative of the first. Okay, so don't forget that you'll have to use the chain rule. Okay. All right, so let's look at an example for the cardioid. R equals 1 plus sine theta. We want to find the slope of the tangent line when theta is pi over 3, and then find the points on the cardioid where the tangent line is horizontal or vertical. So let me go back to okay, so we're thinking about this cardioid. So let's have this in our mind when we'll come back and results and make sure that they kind of match our picture there. Okay, so let's start by finding the slope of the tangent. Now that this is our polar equation, but we want to convert that to a parametric equation, so we want to have an equation in terms of the parameter theta. Okay, so we know that x is going to be r cosine theta. In this case, r is 1 plus sine theta, and then times cosine of theta. So that is our equation for x. Then our y is going to be r sine theta. Again, r is 1 sine theta. And then this time we're going to multiply that by sine theta. Okay. So in order to find the derivative dy dx, we need the derivative of y. So we're going to look at this one at the top. Okay. I'm just going to yeah, let's go ahead and practice using the chain rule, I guess. Okay. Okay, so we're going to do the first, which is 1 theta, times the derivative of the second, which is cosine theta, plus the second, which is sine theta, times the derivative of the first, which is cosine theta. Okay. And then in the denominator, we're going to do this derivative. So we'll do the first times the derivative of the second plus the second times the derivative of the first. Okay, so let's simplify this a little bit. We have here cosine theta plus sine theta cosine theta plus sine theta cosine theta. And in the denominator, I'll just think of this as negative sign. So we've got negative sine of theta minus sine squared of theta plus cosine squared of theta. Okay, so this is cosine of theta plus 2 sine theta cosine theta. Negative sine of theta, and I'm going to switch the order of these, plus cosine squared sine squared theta. Okay, so that's kind of nice because a trig identity for this one. So this is the same thing as sine of 2 theta. And then cosine squared is the same thing as cosine of 2 theta. Alright, so that's a nice expression for our derivative. Okay, and then now that we have we want to find the slope of the tangent line when theta is pi over 3. So we just need to stick over 3 into this equation to get the slope of the tangent line. Okay, so at pi over 3, we're going to have cosine of pi over 3 plus sine of 2 pi over 3 over negative sine of pi over 3 plus cosine of 2 pi over 3. Okay, let's see. Cosine of pi is half. Sine of 2 pi over 3 is a negative number, that's square root of 3 over 2. Okay, negative sine of pi over 3 is negative square root of 2. And then cosine of 2 pi over 3, cosine is negative in the second quadrant, so this is negative 1/2. Okay, multiplied this by 2 over 2, we would get 1 plus the square root of 3 over negative square root of 3 minus 1. Okay, so notice if I factored out a negative, okay, then I've got 1, 3 in the denominator, 1 plus the square root of 3 in the numerator, so this just simplifies to negative 1. That is the slope of the tangent line. at when theta is pi over 3. All right, so that takes the first question, and now we need to go on and look at part B. So we want to find the points where the tangent line is horizontal and where it is vertical. Okay, so let's go ahead and horizontal first. So of course we know, look at when is the derivative equal to 0. Well, that derivative is equation for it, so let me put that in there. We want to look at when cosine of theta plus sine of 2 over negative sine theta plus 2 theta. When is that equal to 0? Okay, well, it will be equal to 0 when the numerator is equal to 0 but the denominator isn't. So we need to actually go ahead and look at both when the numerator will be 0 and when the denominator will be 0, so that we can eliminate any situations where they're both 0. We'll have to consider those specially. Okay, so let's look at the numerator first. So where we have cosine of theta plus sine of 2 theta being 0. Okay. Of this equation, probably is better to go back to cosine theta and substitute 2 sine theta cosine theta in for this one. Then we can factor out the common cosine. So that'll be cosine of theta times 1 plus 2 sine theta. So we need to see where the cosine of theta is 0 or where the sine of theta is equal to negative 1/2. Okay, so the cosine of theta is at pi over 2 and at 3 pi over 2. And then the sine is negative 1/2. Well, that's going to be in the third and fourth quadrants, right? Pi over 6, because it's negative in the third and fourth quadrants. Okay, so that's where the numerator is 0. Let's also look at where the denominator is 0. Let me label this for us. Numerator 0. Let's look at the denominator 0. Okay, so negative sine theta plus cosine 2 theta is 0. Okay, so for this one, we probably want to substitute in 1 minus 2 sine squared of theta. Because that puts everything in terms of sine, and we can factor that. Let's also multiply everything by negative 1. So this should change to a positive, this to a negative, and this to a positive. Rewrite this: 2 sine squared theta plus sine of theta minus 0. Okay, so I should be able to factor this now. Put 2 sine theta here and theta here. Okay, and I know that I have to have a 1 and 1. I want this one to be positive, so I need the 2 to be bigger and the 1 to be smaller. So that gives me sine of theta is a half, or sine of theta is negative 1. Okay, well, the sine of theta is positive 1/2 in the first and second quadrant, so that will be at pi over 6 and 5 pi over 6. And then sine is negative 1 at 3 pi over 2. Okay. So the only overlap we have between these two, okay, is circle these in a different color so we can keep an eye on them. The only place where both the numerator and the denominator are 0. So in terms of horizontal, where only the numerator is 0 and not the denominator, we've got at pi 7 pi over 6 and 11 pi over 6. And I think this says find the points. And so let's look at the point here. When we put in for theta, okay, our R value, our R is going to be 1 plus the sine of pi over 2. The sine of pi over 2 is 1. This is going to be 2. So that will be that point. At 7 pi over 6. Okay, the R is going to be 1 plus the sine of 7 pi over 6. Okay, so that's going to be 1 minus a half, which is half. And then 11 pi over 6. Our R value is going to be 1 plus sine of 11 pi over 6. Again, 11 pi over 6 gave us a negative 1/2. So this one's also a half. Okay, so these are the places that we've got horizontal tangents. Okay, now if we go and look at our example back here, think about whether this seems right. So at the point 2 pi over 2, so here's the angle of 2, sure enough, we have a horizontal tangent. There at this point, this is the point 2 pi over 2. And then we've got 7 pi over 6, 1/2. Okay, so 7 pi over 6 is going to be, over in here somewhere, 1/2. So that's this point right here where we have a horizontal tangent. Is that 1/2, 7 pi over 6. And then also at this 1/2, 11 pi over 6. 11 pi over 6 is over here. Okay, so we've got a horizontal tangent here as well at 1/2, 11 pi over 6. So those do match up with our pictures. Okay, so the horizontal tangents, and let's now look for our vertical tangents. Okay, let me okay, so our vertical tangent, so that where we have a denominator of 0, so we definitely have over 6 and 5 pi over 6. It's this 3 pi over 2 one that we're going to have to work for a little bit. So in terms of points, definitely the pi over 6 and the 5 pi over 6. Let's figure out the R values that go with the look a little into that overlap where both the numerator and the denominator are 0. Okay, so here is going to be 1 plus the sine of pi over 6. Okay, and the sine of pi over 6 is a half, so this gives us 3/2. And then this one is going to be 1 plus the sine of 5 pi over 6. Again, the reason we chose 5 pi over 6 because it's a half, so this is 3/2 as well. Okay. Okay, and then we need to look at the 3 pi over 2. Okay, well, we need to look at this, okay, when theta is 3 pi over 2. Okay, we need to look at the limit as theta approaches 3 pi over 2. The derivative, cosine of theta plus sine of 2 theta over negative sine of theta plus sine of 2 theta. And really we should look at the right and left separately, but let's say we had to do it from the right and from the left and see what happens since we have a 0 over 0. Okay, so if I put 3 pi over 2 in, I'm going to get 0 over 0, but we know from L'Hopital's rule that I can just take the derivative of the numerator and the derivative of the denominator, and I'll get the same limit. So this will be the same thing as the limit as theta approaches 3 pi over 2. Look at the going from the left or from the right. And then the derivative of this one, let's see, the derivative of cosine, negative sine. The derivative of sine of 2 theta is 2 cosine theta. And then in the denominator, the derivative of sine is cosine, so this is cosine. And then the derivative of cosine of 2 theta is negative 2 theta. Okay. And so if we substitute 3 over 2 in the denominator, let's see what happens there. So the cosine of 3 pi over 2 is 0, so this one goes to 0. And the sine of 3 pi over 2, oops, it should have been a 2. So the sine of 2 times 2, or the sine of 3 pi is 0, so this one also goes to 0. Okay, so we still have a 0 in the denominator. What about the numerator? Okay, well, if we're approaching, so let's see, sine of 3 pi over 2, negative 1. Whether I approach it from the left or the right, this one's going towards negative 1. Okay. And then the cosine of 3 pi, the cosine of 3 pi is approaching negative 1 as well. Yeah. And so this is approaching, not 0. It's approaching negative 2. Okay. And so, we have to multiply that by 2. So this one's approaching negative 1 times this is approaching negative 2. Okay. And so we will indeed, we have a 0 value in the denominator and a 0 in the numerator. This is going towards infinity. It could be a positive infinity or infinity depending on whether you're approaching from the left or right, but at least we know it's going towards infinity. Okay, and will indeed be a asymptote, and so let's put our 3 pi over 2 in there. Okay, and our value 1 plus the sine of 3 pi over 2. Okay, so the sine of 3 pi over 2 is negative 1 plus 1 is 0. Okay, so these should be the points where we have vertical asymptotes. All right. So let's compare that with our here. So at pi over 6, 3 pi over 2. So let's say, pi over 6, 3 pi over 2 out here. Okay, so this is our 3 halves pi over 6. There does appear to be a vertical asymptote there. And then 3 halves pi over 5 pi over 6, that's over here. Here's our 3 halves 5 pi over 6. Okay, there is a vertical asymptote. And then our 0, 3 pi over 2, that's right here. So there's this, sharp point right here. This is our 0, 3 pi over 2. It does appear to be a vertical asymptote there as well. Okay, so all of what we did here does indeed match up with our diagram, with our graph over here. It looks like we did everything correctly. Okay. We'll go ahead and work the end of the chapter in another video. So I'll see you next time.